Chapter 1 Chemical Foundations. The outline for this chapter is chemistry, scientific method, units of measurements and uncertainty, sig figs and calculations, dimensional analysis, temperature, classification of matter. Chemistry is the science that seeks to understand what matter does by studying what atoms and compounds, that is, chemicals, do. Atoms and compounds are tiny particles that compose all common matter. Matter is everything around us that we see, touch, and so forth. Atoms, by the way, are bonded together to form compounds. Virtually everything around you is composed of chemicals. Your hand is composed of proteins and lipids and tissue of all sorts. Within your skin, within your cells, in the nucleus, are DNA. And we see a diagram of the double helix structure of DNA. And that is one huge molecule composed of atoms. The pencil lead, which is not lead at all, it's actually a mixture of graphite and some other material. It is composed of chemicals. Graphite is a form of carbon, which looks like that lattice, that cube structure shown in the bottom right. You might be drinking some soda, and it is composed of mostly water with some flavoring agents, including sugar, which is shown in the blow-up picture on the bottom left. It's the big molecule composed of black and white and red and blue balls. The water within your soda is, in the diagram, the bent-shaped molecule that is white, red, and white. Also within your drink is CO2 molecules, and those are what make it fizzy. And in the diagram, those are shown with the linear structure that is red, black, and red. So chemicals are all around us, and how the chemicals will behave in the situation they're in basically is determines what the matter composing them does. We could ask why a soda fizzes. Well, that's due to the CO2, the carbon dioxide, the model that is red, black, red, and those want to be gases, so they collect in a little bubble, and that bubble then comes out because it rises out of the liquid, and if it takes a little bit of liquid with it, it causes it to fizz out a little bit. You feel the fizziness on your tongue from the CO2 bubbles. So understanding what the matter is composed of allows us to understand why it does what it does. Our next topic is the scientific method. Chemists use the scientific method, which uses observation and experimentation to understand nature. So a flowchart of the scientific method is shown on the left in the table, and it starts with our making an observation, maybe more than one observation, and from that making a hypothesis, which would be some sort of a beginning interpretation of what we're seeing. And next would come experiments, so testing out our hypothesis. If our hypothesis seems to hold up through all the different experiments, then that hypothesis is graduated to a theory, which is our best description of what's going on. A law summarizes the results of a large number of observations. More and more experiments are done to very much verify our hypotheses, and that then is our very systematic method of understanding nature. So some definitions for these terms: observations involve measuring or observing some aspect of nature. Observations are something we see and are qualitative, for example, color, or quantitative, and that would mean a number and a unit, a measurement. Some observations can be made with the naked eye. Others emerge from experiments that rely on the use of sensitive instrumentation. Hypotheses are tentative interpretations of the observations. Why is what we are observing happening? Experiments are what we perform to make observations. They are tests of nature to see if a hypothesis is correct. If the hypothesis is not confirmed, it is revised and tested through further experimentation. So as we learn more by doing a variety of experiments, testing out an idea, a hypothesis, then we modify our hypothesis. It becomes more complex often as we go. Laws summarize the results of a large number of observations. A law is a statement that has never been violated in nature. So a law is just a statement of observations. It's not saying why that's occurring, but it's just stating that it is occurring, that it occurs this way. Theories are models that explain and give the underlying causes for a large number of observations and laws. A theory is a powerful statement in science. Laws and theories must be tested and validated by experiment. Science is backed up by experiment. We can make all kinds of theories we want, but they are only as good as the experiment allows them to be. And we can never be sure of whether a theory is correct or not. It's just our best educated guess. So here's an example using the scientific method. What caused the dinosaurs to become extinct? So an observation is the locations of fossils were studied, so where they are, and they're found in a thin dust layer. The hypothesis from that is a large asteroid hit the Earth and blocked the dust created from that impact, blocked the sunlight, and plants died from lack of sun, and subsequently dinosaurs died. Further experiments in the thin dust layer where the fossils were found, there are isotopes of osmium, niobium, and iridium that are not typical Earth amounts. And a crater was found in the Yucatan Peninsula, that's off of Mexico, that could be caused by this large asteroid. This crater is, I think, around 100 miles in diameter, which would mean the asteroid was around 6 miles in diameter. So with the the experiments so far able to be done, the data taken and so forth, the theory then emerges that a large asteroid caused the dinosaurs to become extinct. We can never be absolutely sure what caused the extinction of the dinosaurs. A theory is just our best guess, and it is not always universally accepted. Some scientists still think that a health epidemic or a change in the magnetic field caused their extinction. And by the way, not all great discoveries occur by this scientific method, this very systematic method. Post-it glue was discovered by chance as a chemist was working on something else. Alrighty, so here's an example. Throughout the handout notes, I have examples. Sometimes the answers are given right with the example. Sometimes they are given at the end of the handout in the answers section. So here's an example where the answers are not given right with it. So either stop the video now and come up with answers and then check your answers later, or come back to this by looking at the video again or simply looking at the handout to do this problem. But the problem is classify each statement below as a law, a theory, an experiment, a hypothesis, or an observation. So our first one is ice always floats on water. Okay, so do all of those and check your answers in the back in the answers section. Our next section is units of measurement and uncertainty. We'll first talk about units of measurement. Quantitative observations contain numbers and units. Common measurements in units. Mass. We will often be measuring mass in a chem lab. Units could be kilograms, could be grams, could be milligrams. In our everyday life, we might measure our weight in pounds. That would be in the British system. We use the metric system in science. We'll be measuring length in meters, centimeters, millimeters. In our everyday life, we might measure length in miles. Time, we measure time in seconds usually. Temperature, we measure in degrees Celsius in a science lab. Maybe in our everyday life, we use degrees Fahrenheit. When we make calculations, we have to convert from degrees Celsius into Kelvin. The amount of a substance present, usually we're working in a unit called moles. Volume, meters cubed, centimeters cubed. In fact, 1 cubic centimeter is 1 milliliter. In our everyday life, we might be measuring in gallons or cups. Density, another quantity that we work with, and that has units of grams per milliliter. Here's a table from your textbook with a little bit more on physical quantities. In America, we are exposed to two systems of measurement. The metric system, when we're working in our science classes, and the British system at home. The metric system, that is the one that we will pretty much use exclusively in our science classes. And it is very handy because it is based on multiples of 10. We have our base unit. Above it, we have deca. Above that, hecto. Above that, kilo. And they're going up by an order of magnitude of 10 each time. So 1 kilogram is 1,000 grams. 1 kilometer, which we might pronounce kilometer, is 1,000 meters. So whether we're working in grams or meters, we have the same conversion when going from the base to kilo. That same is true, of course, going down. Going down from the base, we first have deci, and then centi, and then milli. That is to say, 100 centimeters is 1 meter. 100 centigrams is 1 gram. Milli is the one below that. 1,000 milligrams is 1 gram. 1,000 millimeters is 1 meter. Below that, several more orders of magnitude, we have micro. Some orders of magnitude below that, we have nano. 10 to the 9th nanometers is 1 meter. 10 to the 6th micrograms is 1 gram. The ones that are most common are shown in this table in blue, and I want you to commit to memory: kilo, centi, milli, micro, and nano. The British system, so that's what we use in our everyday life, at least here in America, though most countries in their everyday life use the metric system. Anyway, here we're having a hard time converting over. The British system is what you're exposed to, most likely at home. That's the one where, for example, 3 teaspoons equal 1 tablespoon, 1 mile is 5280 feet, 1 cup is 8 ounces, etc. Notice there's no commonality between those different units, unlike the metric system, which is based on orders of 10. Okay, next we will have the uncertainty in measurements section. When reading the volume using a burette, for example, we read at the bottom of the meniscus and report the certain digits and the first uncertain digit. Okay, so a burette is a long, skinny piece of glassware that we use to make titrations. And we see what it looks like in the diagram on the left. And we see that the liquid in it is somewhere between 20 and 21 mLs. In our blow-up picture, we see that the liquid, the bottom of the meniscus, is between, of course, 20 and 21, and then within that, between the first and second line. So what we see with certainty is the liquid is 20.1, and then we read between the lines. We break the first to second line up in our mind's eye into 10 equally spaced divisions, and we decide where in there that bottom of the meniscus is. Perhaps one person sees it as 20.15 mLs. Perhaps the second person said, no, it's more like 20.14. Perhaps the third person sees it as, no, 20.13 mLs. So it's the 5, the 4, the 3. Those are the uncertain digit, but it's better to report that than not. But everybody would agree on the 20.1 part. So we have there, we're reporting 4 digits, and our uncertainty is to the last one. So our uncertainty is plus or minus 0.01 ml. Precision and accuracy, there's a slight difference between those two terms. They both describe the reliability of measurements. The slight difference comes in by these definitions. Accuracy refers to the agreement of a measured value and an accepted true value. So a measured value would be the one, for example, we would make in the lab, and then we compare it to the accepted true value. The closer we are, the better is our accuracy. Precision refers to the degree of agreement among several measured values. So often we don't have an accepted true value. So we make many measurements, and the closeness of those measurements gives us confidence that probably we've done a good job, and our value, that our measured quantity, is going to be pretty right on. Here's an example that shows the results of several dart throws and also shows the difference between accuracy and precision. So the purple ones, those are pretty much far from hitting right spot on. They also are quite spread out. So we would say they're not accurate and the precision is low. The middle one, the red darts, those are not spot on, so the accuracy is low, but at least the precision is fairly high because they're close together. In the green dart example, they're spot on, they're very close to the accepted true value, and also they're very close to each other. So we would say they're both accurate and precise. Precision is often used as an indication of accuracy. We average the data to get the best value, and this is okay as long as any systematic error is small. Okay, our next section is on sig figs and calculations. So sig figs is an abbreviation for significant figures. They are digits expressed in a number. They represent the accuracy with which the measurement was made. So let's say that we have been asked to measure the length of a table and report that to somebody else who doesn't see our measuring device and also doesn't see our table. So through our description, we have to indicate how accurately we made this measurement. So we report the value that we measure to that person. Now, the number of digits that we report in our measured quantity is a reflection of their accuracy. And when we are not the one making the measurement, we're the one receiving the measured value, we look at the number, of course, to see how big it is, what the units are, etc., but also to get a sense of how accurately that measurement was made. So we have rules for looking at a number and determining its accuracy by determining its number of sig figs. So we have the rules for counting sig figs. They mean looking at a number and determining how many of the numbers within that number are significant. How accurate is that number? And again, all that's determined by counting the number of sig figs in it. So here are the rules for counting sig figs. All non-zero numbers are significant. So if our measurement that we are given is 143, we would say it has 3 sig figs in it because they are all non-zero numbers. The number 7854.98 has 6 non-zero numbers in it. They are all significant. So this 7854.98 has twice as many sig figs. It's not only bigger than the other number, but it has more sig figs in it, therefore it's a more accurate measurement. It's made using a better measuring device, most likely. Our second rule is sandwiched zeros are significant. Those are the zeros in between non-zero numbers. So if we have the measurement 2002, those two zeros are between non-zero numbers, so those are significant. So we would say that number has 4 sig figs in it. The number 60203 has 2 sandwiched zeros. It has 5 sig figs. Leading zeros are not significant. Leading zeros are the zeros before any non-zero numbers. They are placeholders. They're just telling us how small the number is. So the number 0.00369 has the first 3 zeros, the only zeros in it, in fact, those are all leading zeros. Those are not significant. So that number only has 3 sig figs. The number 0.0412 has 3 sig figs also. The 2 zeros are leading. They are not significant. The number 0.009067 has the first 3 zeros, leading zeros, not significant. The 0 between the 9 and the 6 is a sandwiched 0. It is significant, so that number has 4 sig figs. Our next rule, trailing zeros. Those are zeros after non-zero numbers. Trailing zeros are significant if there is a decimal point. Trailing zeros are not significant if there is no decimal point. So in the number 100 point, we have the decimal point. Those zeros are trailing zeros. Because of the decimal point, they are significant. And that is our way in science of being able to convey to somebody that we have the number 100 and all of the numbers within it were very accurately obtained. The number 100 without a decimal point, that's just a measurement that is approximately 100. Maybe it's really more like 90, or maybe it's really like 110, but it's about 100. It's that order of magnitude at least. So it's not very accurate. We would say it only has 1 sig fig. So here's an example for you to do. How many sig figs are in those next 4 numbers? So come up with answers and check your answers in the answer section. Exact numbers. So those have an infinite number of sig figs. Those we can think of as completely accurate. Like counted numbers. How many marbles are there in the box? Let's say we count easily to have 15 marbles in the box. Well, we are sure of that. We would not say that we're unsure at all. We don't have 14, we don't have 16, we have 15. So that would be a very accurate measurement. We call that exact. How many donuts in a dozen donuts? Well, we have 12 in our box of donuts. How many students in a class? Maybe 24. Again, we're sure of that. We're sure of our counting there. Defined numbers. We will see that we make conversions often in chemistry. We might convert from inches to feet, for example, if we're doing some kind of conversion using the British system. That is a defined quantity. Somebody a long time ago decided how long an inch would be and that there would be 12 of them in a foot. That there are 3 feet in a yard, again, the British system, but that's also a defined quantity. Somebody made that up. All of the metric system conversions are exact. They are defined. They are made up. They're not based on measurement. That is, how many grams are in a kilogram? That's exact. Rules for calculating with sig figs. So let's say that that person who wanted the length of the table actually doesn't want only the length, they want the area. So we have to make a measurement of the length and the width of the table and multiply those two quantities together and report that area to the next person. So we're making calculations with our sig figs, and yet our calculated value has to reflect the accuracy that each of those individual measurements were made. So here are rules for calculating with sig figs. If we're doing multiplication or division with our measurements, we determine the amount of sig figs in each number, and the answer is the least amount of sig figs of the number. That is, if one of our measurements is very accurate, but the other one for some reason is not, when we go to calculate with those two, the less accurate one is going to lower the overall accuracy of our final answer. So let's say that we made a measurement of a length to be 3.30 centimeters and another length to be 4.7 centimeters, and we're multiplying those two because we want to find the area. Well, perhaps on our calculator we would see 15.51. What are we going to report though? Well, looking at 3.30, we have 3 sig figs. 4.7, we have only 2 sig figs, so we can only report 2 sig figs in our final answer. So we look at the 15.51, we keep the 1, we keep the 5, those are 2 of our sig figs that we will keep, but then we will have to drop the 5 and the 1. Now, we look at that first number that we're dropping, the 5 in this case. Is it 5 or greater? If so, we round up. So, of course, 5 is 5 or greater. So we don't report 15 centimeters squared, we report 16 centimeters squared. Notice when we multiply numbers, we also multiply units. Centimeter times centimeter gives us centimeters squared. Okay, so when rounding 0 to 4, we leave as is. 5 to 9, we round up as we did in that example. So here's some examples for you to come back to later and check your answers. Our next example is if we were multiplying the two measurements 2351 and 318 together on our calculator, we would, for example, see 747618. But we see in our measurements that we have to round that number to 3 sig figs. So we keep the 7, we keep the 4, we keep the 7. We have to get rid of the 6, the 1, and the 8. But we can't just drop them because we're not talking about a number around 700. We're talking about a number around 700,000. So what we do is we replace those last 3 numbers with zeros, so they're just placeholders. Now notice that the 6 that we're dropping is 5 or greater, so what we will do is round that 7 up to 8, and we'll report 748000. The rule for addition and subtraction is, notice it's different than the rule for multiplication and division. So addition and subtraction, what we do there is we determine the amount of decimals, not overall sig figs, but decimals in each answer. The answer has the least amount of decimals of the numbers. So what we're doing is looking at decimals. Remember that decimals are the numbers to the right of the decimal point. So let's say that we are subtracting these two numbers, 2.443 meters and 0.213 meters. So 2.443 minus 0.213. In our calculator, we might see 0.23 because 3 minus 3 is 0, and the calculator doesn't necessarily show that. But what we have to realize is if we had 3 decimals in each of our original numbers, we're going to want 3 decimals in our final answer. So what we're going to report is 2.230 meters. That is to say, it's as if we're making that final measurement, 2.230, using whatever measuring device we used to make the other 2 measurements, which was a measuring device that allowed us to have 3 decimals. Our next example is 7.6500 grams plus 0.1 grams. So we made that first measurement on a very accurate balance. The second measurement was made on a balance that's not very accurate. It only has accuracy of 1 decimal. So in our calculator, we might see that sum to be 7.7500 grams, or maybe we would just see 7.75. But what we have to realize is we only have 1 decimal in one of our 2 numbers, that's 0.1. The other number, we have 4 decimals, very accurate, but the lower accuracy number is going to greatly reduce the accuracy in our final answer. So we have to drop, we can only report 1 decimal, so we're going to report the 7.7, getting rid of the 500, but the 5 is 5 or greater, so we round our answer up to 7.8 grams. So here's an example for you to work on, come back to, check your answer. Next we have when we combine operations, when we do subtraction and multiplication, division, addition all together. So let's say that we have this 78.6 minus 69.5 that we then divide by 4.342. They're all measurements, so we have to think about sig figs and so forth. So just as we would do the subtraction first, we do that and then we think about sig figs for it. So 78.6 minus 69.5, that gives us 9.1. Notice we went from 3 sig figs down to only 2. Well, but we've done it correctly because we are doing subtraction. With subtraction, we think about decimals. 78.6, 1 decimal, 69.5, 1 decimal. So our answer is going to have only 1 decimal. What comes on the left side of the decimal point just depends upon the difference between the 78 and the 69. Okay, so now we have 9.1 that we're dividing by 4.342. So we have 2 sig figs dividing by 4 sig figs. Our answer can only have 2 sig figs in it. So although when we do that division, we might see 2.096 in our calculator, we have to round that to 2.1. Scientific notation. It's a way of writing a very big or very small number. And in scientific notation, the number that appears first is between 1 and 10, and then multiplied by 10 raised to the necessary power. Okay, so let's say that we have the number 233. Now, indeed, that isn't a very big number. We would probably not report that in scientific notation. We would just use this standard notation, this ordinary notation. We would just write 233. But to see how we would convert to scientific notation, we will run through this example. So 233, that's equal to 2.33 times 100. And then what we do is we make that 100 into 10 squared. Now, 2.33 times 10 squared, that is the number 233 written in scientific notation. This number here, 2998, with all those zeros, meters per second, that's a very, very large number written in standard notation. It's kind of easy to lose how many zeros there are. How big is that number? So we would write that in scientific notation. What we would do is take that invisible zero take that invisible decimal point after the last zero and count how many digits we have to move it over to get it between the 2 and the 9. We would have to move it over 8 places. So this very large number becomes 2.998 times 10 to the 8th. Units are meters per second. So it becomes that in scientific notation. It's much easier to look at that number and get a sense of how big it is. Notice that the number 299800000 has 4 sig figs. All those trailing zeros are not significant because there is no decimal point. By the way, that number is to 4 sig figs the speed of light. So that means our number in scientific notation also has to have 4 sig figs. And it does. So sig figs in scientific notation are counted in not the times 10 part, but only the pre-number, the 2.998 in this case. We can also write very small numbers in scientific notation. This number 0.0000741 kilograms is equal to 7.41 times 10 to the minus 6 kilograms. So what we do is we take that decimal point in the standard notation and we move it to between the 7 and the 4. We had to move it 6 places, and so that's why we have times 10 to the minus 6. Notice we have minus 6, and that is because we have a very small number. This 7.41 times 10 to the minus 6 is a positive number, and I'm trying to emphasize that by showing the number line and the arrow there. Indeed, it's a very small number, but it's a positive number. That times 10 to the minus 6, the minus is the exponent. And our number has 3 sig figs. All those leading zeros in the standard notation are not significant, they're placeholders. So the 741, those are the only sig figs, so we have 3 sig figs. Next, we look at using our calculator. Most of you, I imagine, have a TI calculator, a graphing calculator. So why don't you stop the video, get your calculator. All right, so once you have your calculator, before you type anything into it, let's look at this number. We have 1.0 times 10 cubed divided by 1.0 times 10 cubed. So what we have is 1,000, good to 2 sig figs, divided by 1,000. 1,000 over 1,000 is equal to 1. Sig fig wise, we would write that as 1.0. Now, how do you enter that in your calculator? So you would type 1.0, then find the double E key. 1.0 hit the double E key, and then hit a 3. That is how you enter a number in scientific notation into your calculator. So 1.0 double E3, hit the divide key, 1.0 double E3, and then enter, and you should see 1. Do not type that number as 1 times 10 caret 3 divide 1 times 10 caret 3, because what the calculator will do is it will take your 1 times 10 cubed and have 1,000, and then it will divide that by 1, and it will multiply that all by 1 times 10 cubed, and it will report the answer as 1,000. Use the double E key. That keeps the number 1.0 times 10 cubed. That keeps that number as a single number, because it really isn't 1 separate from 10 cubed. It's that whole number together. Our next section is on dimensional analysis, and that we will be using a lot in chemistry. And it is a method that converts units. To use this method, what I will first introduce to you is our exam equation sheet. So the exam equation sheet, which is here, it's not in its complete form here. It's in its complete form in Canvas in a module called exam equation sheet. So go in there, and that's where you'll have the exam equation sheet. I would advise that you print that out so that you have that with you as you do problems in the handout, problems in the homework, problems on quizzes, etc. So in the first part of the exam equation sheet, I have a number of conversions. 1 inch is 2.54 centimeters. That's exact. And 1 calorie is 4.184 joules. A lot of this you might not be familiar with now, but you will as we go through our course. So the first part is conversions, very handy for when we do dimensional analysis conversions. The second part is on constants. M sub E, that's the mass of the electron, that's 9.109 times 10 to the minus 31 kilograms. We have a lot of different constants in there that you will work with as we go through the semester. And next we have equations. So those are converting between, well, not necessarily converting, they're just equations. So you will look in here to find equations as needed for various calculations. The last part of it that isn't shown here is the solubility rules that we will get to in a future chapter. And those are, of course, in the exam equation sheet that is in your in Canvas. Okay, next we have some examples for us to work with dimensional analysis. So our problem is how many kilometers are in 24,000 meters. So what we do is we start with our initial given quantity, 24,000 meters. I put it over 1 just to emphasize that it's in the numerator, 24,000 meters. You can skip that over 1 part if you would like to. The conversion that we need is the conversion between meters and kilometers, and it is 1,000 meters are 1 kilometer. And notice that we're going from meters to kilometers. So we're wanting to get rid of meters. So what we do in our conversion is we put the meters in the bottom and we put kilometers in the top, because when we do the multiplying and dividing, we have meters over meters, meters go, and we have just kilometers left. So we take 24,000, we divide by 1,000, we get 24, and our unit kilometer. 24, 2 sig figs, because that's how many we started with. Alrighty, so here's some conversion problems for you to work with. So come back to those later, check your answers. Here's one that has us use several conversions. How many feet are in 100 point meters? So 100 point, that means we have 3 sig figs. So we start with our 100 meters, and to use the conversions that are on the exam equation sheet, what we would do is, for example, go from meters to centimeters. In that way, meters have canceled out. And then from centimeters to inches, now centimeters have canceled out. And then finally inches to feet. And then inches cancel out. Now notice that we always write our conversions such that the one unit we're wanting to get rid of through the use of our conversion is in the denominator of our conversion. So we have meter over meters, that's gone. And then we have centimeter over centimeter, that's gone. Inch over inch, that's gone. And our final unit is feet. Okay, so then in our calculator, we would type 100 times 100 divide 2.54 divide 12. We can ignore multiplying and dividing by 1 because that won't change our answer any. So in our calculator, we might see, for example, 328.084, which we would round to 328 feet. So here's another problem for you to work on. Density. Density is a property that allows us to identify substances. Density is defined to be mass per volume. Something very dense has a large mass for its volume. Something with a very low density has a very light mass for its volume. The more dense something is, the more it settles to the bottom. Density is a measured quantity, so we definitely have to think about sig figs with it. So here's an example. A piece of titanium, which is a metal, it's an element on the periodic table, has a mass of 10.1 grams and occupies a space of 2.25 milliliters. What is its density? So density is mass over volume. Notice how I write out the equation, yes, and then I put the terms in, 10.1 grams for mass, 2.25 mLs for volume. So we end up with dividing 10.1 by 2.25, and we get 4.49 to 3 sig figs. Our units, none of them cancel out, so we have simply grams per ml. 1 milliliter is 1 cubic centimeter, so the density is also 4.49 grams per cubic centimeter. Here's an example for you to do and check your answers for later. Density is a bridge between mass and volume. That is, we can use it in the right application as a conversion. Here's an example. Ethanol has a density of 0.785 grams per ml. What is the mass of 20.0 mLs of ethanol? So we take that initial measured quantity that we're given, 20.0 mLs, and we use the density as a conversion to go from mLs to grams. So we write the density such that milliliters will cancel out. So we put the ml, the 1 ml in the bottom, and the 0.785 grams in the top. MLs cancel, so we multiply 20.0 by 0.785 and get 15.7 to 3 sig figs, and our unit is gram. And here's an example for you to do and check your answers. Our next section is on temperature. Temperature is, for us in our everyday life, a reflection of how cold or warm the day will be, how comfortable will we be, what do we have to wear, what can we do given the temperature. In science, it very much is a measure of the random energy, the random motion of the particles in whatever it is we're measuring the temperature of. If it's a hot object we've measured the temperature of, then the particles within that material have a lot of motion. If it's cold, then their motion is slower. So even though you might look at the table or the chair you're sitting on and think, well, nothing's moving, on the molecular scale, there's a lot of motion. And the hotter is the chair, the more fast the particles within it are moving. We have 3 common scales for making temperature measurements. We have in our everyday life the Fahrenheit scale, and in that scale, water freezes at 32 degrees and boils at 212. In science, we measure almost always in the Celsius scale, and in that one, water freezes at 0 degrees and boils at 100 degrees. When we make calculations, usually we have to convert from Celsius to a unit called Kelvin. You will see the conversion shortly, how to do that. In this unit, the water freezes at 273.15 Kelvin and boils at 373.15 Kelvin. We have something called absolute zero, and nothing can get colder than absolute zero. In the Kelvin scale, it is 0 Kelvin, so we never have a temperature that is negative in units of Kelvin. In degrees Celsius, the lowest temperature attainable is negative 273.15 degrees Celsius, and in Fahrenheit it would be negative 459.7 degrees Fahrenheit. So temperature depends on how fast particles move. The more slowly they move, the colder the substance becomes. At absolute zero, molecules stop moving altogether. And since it's not possible for the particles to move more slowly than not moving at all, the temperature cannot get any lower than 0 K. And that's why this is called absolute zero. So here's equations for converting between units. So to go from Fahrenheit to Celsius, we use the first conversion. From Celsius to Fahrenheit, the second, and then from Celsius to Kelvin, the third. In our first 2 equations, the ones involving Celsius and Fahrenheit, the 5, the 9, and the 32 are all exact, so they will not limit us on sig figs as we're making conversions in those units. In fact, what we do is we just look at decimals. However many decimals we start with is the number of decimals we end with. So here's an example for us. Convert 98.6 degrees Fahrenheit into degrees Celsius and into Kelvin. So that's our average body temperature, although I hear it's gone down a little. So degrees Celsius equals 5/9 times degrees Fahrenheit minus 32. There's our equation. So for the Fahrenheit, we put the 98.6 in. We subtract the 32, multiply by 5, divide by 9, and we get 37.0 degrees Celsius. Notice we start with 1 decimal, 98.6, and we report 1 decimal, 37.0 degrees Celsius. So that would be standard body temperature in degrees Celsius. To convert to Kelvin, we have the equation TK equals TC plus 273.15. So we have 37.0 plus 273.15. We get 310.15, but notice 37.0 has only 1 decimal. So our 0.15, we round to 0.2. So we report 310.2 Kelvin. Here's a problem for you to come back to later. Our next section is on classification of matter. So we can classify matter a number of ways. Here's one way: to classify it based on what phase it's in, what state it's in. Matter occupies space, has mass, it exists in the 3 common phases or states, either as a solid, or a liquid, or a gas. A gas, we could also call it in the vapor phase or the vapor state. The solid and liquid states, those are the condensed states because particles are close together. In our diagram on the left, we see for the solid, the liquid, and these are referring to water, so we see our bent water molecule shown. In the solid and liquid, they're very close together. And that's why we see the liquid water, we see the ice. In the gas phase, they are so far apart that we do not see them. In fact, in our diagram there, the vapor, the gas, we would actually not see it. The particles are very far apart. The individual molecules are not together, so we don't see them. So in the gas state, particles are far apart. That's one way to classify matter. And we very much, as chemists, are concerned with what phase or state is whatever chemical we're talking about in. Another is to classify it as mixtures or substances, pure substances. So we have a flow chart there where we have matter at the top, and matter is either mixtures or pure substances. Let's go to the pure substance side. Pure substances are either elements, and those would be elements on the periodic table, such as chlorine, copper, iron, nickel, sodium, etc. Or they are compounds. Elements cannot be further broken down and still be copper or still be chlorine. Compounds are composed of different elements bonded together. Water is a compound composed of hydrogen and oxygen, where hydrogen and oxygen, those are each elements. Water is the compound, H2O. Another compound that we would get by combining chlorine and copper is CuCl2. And that compound, which we name copper 2 chloride, always looks like that, CuCl2. We always have 1 copper for every 2 chlorines. So those are pure substances. And mixtures, so going to the left side, mixtures come as 2 types: heterogeneous or homogeneous. You might be drinking a cup of coffee or tea right now, And you might have put some sugar or some sweetener in your drink. If you've let it sit long enough, then it's the same throughout. It doesn't taste different at the top as at the bottom. If so, that would be a homogeneous mixture, the same throughout. Now, mixtures are two or more different pure substances. So they are composed of different substances that we could have a lot, like be it very concentrated. Like if we really have a sweet tooth, we might like a lot of sweetener in our coffee. Or we might not like any at all, or we might like only a little bit. So a mixture can have a variable amount of substances in it. Unlike a pure compound, such as copper 2 chloride, that is always CuCl2, no matter what. If we're talking copper 2 chloride, it is CuCl2. Whereas with our coffee or our tea, it might be very sweet, lots of sweetener, or it might not be so sweet, not so much sweetener. So it's variable in its composition. So that's homogeneous mixtures. We can also have heterogeneous mixtures. Like imagine a rock. Some of you might like to go to the Sierra Nevada mountains for hiking. And you've noticed that granitic rock that is white with black and some other different minerals within it. You can visibly see that it's not the same throughout. It's composed of different minerals, different parts. That would be a heterogeneous mixture. In a different part of the Sierra Nevada mountains, it could be that there's a lot more of the white component than the black component. So it's variable. Mixtures are variable. Whereas pure substances, which are either elements or compounds, are not variable. Compounds are combinations of elements. Okay, so that's one way to look at matter. Our last part is on changes. We have, under this section, two types of changes: chemical changes and physical changes. When a chemical change has occurred, a substance becomes a new substance. We've undergone a chemical reaction, like we talked about the pure compound CuCl2. So that's made from combining copper and chlorine. Copper at room temperature exists as that orange shiny metal you've probably seen in terms of copper wiring. Chlorine exists as a gas at room temperature, and it has a slight yellow color to it. So we go from metal plus gas to copper 2 chloride, which looks a lot like salt, like sodium chloride, except it has a green color. It's a grainy substance, so that compound is very different from the elements that composed it. So that's a chemical change, a chemical reaction that has occurred. A physical change is when we have the same substance before as after the change, but it's in a different phase. Like when we take liquid water and boil it to gaseous water, we still have H2O. We have just changed its phase. Or when we melt ice, it's gone from solid to liquid. Same H2O, but just different phase. So that completes our chapter lecture video. Now, what to do is to get the handout and go through all the exercises, check your answers, go through the video again as it helps you. The handout that you will find in Canvas is basically the same as what we went through in this lecture video, minus my voice, of course. and read through chapter 1 in your textbook, the Zumdahl textbook, do the assigned homework problems, and go back and do it all again as you need to. So throughout the rest of these, the handout here, the video included, are just the answers. Alrighty, so that's it then.